Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the chat window. Your questions in the chat window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Mike Johnson from Entegris.
Great. Thanks, Leah, for the introduction, and good morning, everyone. As Leah stated, my name is Mike Johnson, and I'm the Market Development Engineering Manager at Entegris. Today I'll be discussing single-use bags and gas permeation. So let's get started. The agenda for today's presentation includes a permeation overview, a review of the abstract and test protocol, an assessment of the results, followed by a conclusion summary, and some discussion time. Let's start off with the definition of permeation. According to Merriam-Webster, the definition of permeation is to diffuse through or penetrate something. So the image here depicts how molecules, gas or fluid, can move through a solid, such as a film. The red dots depict the molecules, the gray is the film, and essentially you've just got those molecules moving through the material. Permeation rates are a function of the fluid properties. Is it a gas or is it a liquid? The type of material being penetrated, as well as the application temperature. There are a few standardized test methods available through ASTM that are used to determine permeability characteristics. One is ASTM D1434, and another is ASTM D3985. The image on the right shows a schematic of a test apparatus used at Entegris to determine permeation rates through polymers using high-pressure gas. At the center of the test apparatus is a fixture used to hold the sample plaque. Upstream of the plaque is a high-pressure gas, and downstream of the plaque is a sensor used to measure the rate of permeation through the material as well as breakthrough time. This is an image of the actual test apparatus, and although it may not be pretty, it is very effective and allows us to test several different material iterations and to characterize any changes in materials. The current state of single-use bags calls for the utilization of an EVOH layer to provide a gas permeation barrier. The wetted surface layer is sometimes low-density polyethylene, or EVA. The middle layer is the EVOH gas barrier layer, and then the outer layer may be EVA or polyethylene or potentially other polymers. This combination of layers, while it creates a low gas permeation assembly, it raises the risk of detrimental extractables due to the addition of adhesives needed to bond the layers together. This construction is also susceptible to delamination and film failure due to differences in thermal expansion and the challenges with bonding different polymers together. New advancements in films allows for the utilization of a single layer of gamma-stable fluoropolymer to greatly reduce the risk of extractables. The single-layer technology also eliminates any concerns over delamination. But with the elimination of an EVOH layer, how does this approach impact permeation? Before answering that question, let's take a look at the permeation rate of several materials used in single-use bioprocessing. The table shown here shows moisture, oxygen, and carbon dioxide permeation rates for various polymers and elastomers used in single-use assemblies. The first material shown here is EVOH. This material has very low permeation rates for moisture, as well as oxygen and CO2. Next is data on PFA, a fluoropolymer material. This polymer is very good for low moisture transmission, but has a relatively high gas permeation rate for both O2 and CO2 in comparison to the EVOH. Third is data on EVA. EVA is almost 100 times higher in moisture permeation. It's similar to PFA in oxygen permeation, and is quite a bit higher than PFA for the CO2 permeation. Lastly is the silicone material, oftentimes used for tubing on single-use assemblies. As an elastomeric material, silicone has an extremely high permeation rate for both O2 and CO2. So as you can see, permeation rates are quite varied depending upon the material being evaluated. But in the end, what are users of single-use bags looking for? Is it really a permeation rate? What end users are typically looking for is product stability. This often comes in terms of stable pH or a stable concentration. Consequently, the real question isn't what is the bag's permeation rate. The real question is how well does the bag maintain the solution pH or concentration, and how do materials of construction impact this? In order to address these concerns, this presentation will present pH stability data from sodium phosphate solution that has been frozen in single-use bags with different gas permeation rates and placed into chambers with sublimating dry ice that give off CO2. The test included 4 different bag sets. One set is the Aramis single-layer fluoropolymer bag. A second set is a multi-layer EVA, EVOH, EVA bag construction. And sets 3 and 4 were these same bags but placed into Mylar. The solution was a 5 millimolar sodium phosphate mixture. And in this test, the bags were frozen at -85 and then stored in dry ice chambers at -78. pH measurements were taken at time intervals of 0, 1, 3, 7, and 21 days. The protocol is as follows. Prepare a 5 millimolar sodium phosphate solution with a target pH of 6.1. Then we prepared the bags. First, the bags were weighed. The bags were then filled with 1 liter of solution via scale and peristaltic pump. Bags were weighed post-filling, and then a portion of the filled bags were placed into the Mylar bags and vacuum sealed. The filled bags were then placed into a freezer at -85 degrees C to facilitate the freezing process, and this took about 2 hours. The frozen bags were then placed into chambers containing 200 pounds of dry ice each. Specific bags were removed at the test time intervals of 1, 3, 7, and 21 days. The bags were placed in a water bath at 23.5 degrees C to rapidly thaw the sodium phosphate solution. A 30 ml sample was then pulled from each bag, and that was used to measure and record the solution. The change in pH was then determined by calculating the difference between the time 0 pH and the time interval pH. This chart shows the data generated from this evaluation. The yellow line shown here is the Aramis single-layer fluoropolymer bag, and this gray line is the multi-layer bag containing the EVOH gas permeation layer. So if you take a look at these 2 different lines, there's a slight difference at the day 7 time check, but it's quite small. We're looking at approximately 0.15 change or difference between the single layer and the multi-layer bag. And then out here at the day 21 time point, both of these bags had very comparable pH stability. The blue line and the red line shown here are the 2 single-use bags encased in Mylar. These bags do show a slight change in pH, but essentially these bags had a very similar profile when looking at the overall change in pH from one to the other. Round 2 of testing, we eliminated the placement of the bags in the freezer at -85 degrees C. So instead, the filled bags were placed directly into the dry ice chambers, allowing the sodium phosphate solution to freeze while being exposed to the sublimating dry ice. Again, the bags were taken out at day 1, 3, 7, and 21, and their pH was compared to the pH at day 0. Results for round 2 were very similar to the results in round 1. Both bags did experience a drop in pH. The drop in pH was similar between the single-layer fluoropolymer bag and the multi-layer bag with EVOH. Both of these bags had a greater change in pH as compared to the bags placed into the freezer to solidify and then into the dry ice chambers. In conclusion, the changes in pH of frozen sodium phosphate solutions contained in single-use bags, pre-frozen and stored in dry ice chambers at -78 were similar in bags containing an EVOH layer and bags that did not have an EVOH layer. Encasing the single-use polymeric bags with a mylar bag did reduce the amount of pH change, but just slightly. There was a greater change in pH when the storage bags were placed directly into the dry ice chamber, though the changes in pH were similar between the bags containing an EVOH layer and the single-layer fluoropolymer bags. So, based on a 21-day exposure to CO2 from sublimating dry ice, there does not appear to be a CO2 gas permeation performance benefit from the EVOH layer on the stability of frozen sodium phosphate solutions.
Okay, thanks, Mike. So now we have some questions from the audience. So would you expect the same results from other fluids?
I think this is, again, going back to the factors that impact permeation. Other fluids may have a greater tendency to permeate through both of these bags or less. I think it needs to be looked at on really a solution by solution situation here. So I would expect the results to be somewhat similar, but again, it is somewhat solution specific.
And on the study, why did you pick these time points?
So these time points were established kind of taking a look at a common practice of how long the bags might be frozen and then transported, say, within a facility or from one facility to a next. So it kind of was taking a look at that cold chain process and shipping process that bioprocessing fluids might undergo in the industry.
And can you add an EVOH layer to the fluoropolymer material?
I think, first of all, it would be very challenging. So when you start taking a look at different polymers, their melt temperatures, and their ability to adhere to one another, I think there would be some challenges to do that. And I would say also initially looking at the data shown here in the webinar, I don't see the need right now to add that gas barrier layer to the single layer fluoropolymer material. And then you also have to keep in mind if that were accomplished, then you've got an impact on the extractables profile that would be generated from this material due to the adhesive layer that was placed into the construction.
How many bags do you have per time point, and did you see any bag-to-bag variability?
We did 5 bags per time point and took an average of them. And you know, they were really pretty consistent from one bag to the next. So we didn't see any significant excursions or oddball flyers in the group. So it was all pretty consistent data set.
And what is the cooling time difference between different configurations from start to target frozen temperature?
So the cooling time, I think this question is looking at how fast the solutions froze, if I'm correct here. And it took, I believe it's about 2 hours to freeze the sodium phosphate solution, and that wasn't bag dependent. So that time was uniform between the single layer bag and the multi-layer bag.
Okay. And one more question. Okay, would you expect the same results of the bags that were directly exposed to dry ice vapors were placed in a low atmospheric pressure condition comparable to the conditions during shipping on a commercial flight?
I guess the answer that I have to that is I would expect the two products or the two bags that were tested to be similar to one another. I wouldn't see a significant difference between the two products tested, but would there be a difference in the change in pH as a whole? I guess I don't have enough information to answer that one.
Okay. And this last one actually gets at the previous webcast that we've done with you. So the question is, what is the durability difference between the bags at frozen versus room temperature for puncture, tear, etc.?
So I guess in comparing the two bag assemblies, the single layer fluoropolymer and the multi-layer, the single layer is going to have much better strength characteristics at cold temperatures. So at that -78 or even the -85, the fluoropolymer materials have a very, very wide range of usage temperatures. So at -85, there's really no change, very little change, I would say, in the material properties of the fluoropolymer material, where a bag like an EVA, EVOH, EVA layer, you start to see the material get brittle and potentially fracture. So there's a much higher risk at that cold temperature using a multi-layer bag than the single layer fluoropolymer bag.
Okay. Well, I think that's all the time we have for questions today. If we didn't get to your question, they will be passed on to Mike, and he can follow up with you directly. So thank you, Mike, and thank you to our audience for joining us.
All right. Thank you, Leah. Appreciate it.
So the recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcast. Look for those announcements in your inbox. Thanks.